Yes, yes.
And at what time will it be?
So, start in 2 minutes. Hello.
Yes.
I'm Sadik Rangwala. I'm the chair of this session.
Okay.
So the session is going to start in like 2 minutes.
Perfect. Okay, thank you.
Hi, Alan. It's Swapan. I'm here. Thanks.
Hi, good morning.
Great. We'll start in just a minute. There was a coffee break, and as usual, people are slow in moving in. Just
good. I hope they're
thanks
enjoying themselves.
How early is it for you now? 7 o'clock in the morning?
Here it's 7:20. Yes. Yeah.
Okay. Thanks a lot. Thanks a lot for staying up. Okay, yes.
No problem.
Okay, Sadiq, I give it to you. Let's start.
So welcome back, everyone. Now we have a talk by Alan Caldwell from MPI Munich, and he's going to talk about plasma wake field acceleration and awake.
Okay, so everybody can see my slides?
Yes, we can see your slides.
Okay, so I should start. Okay. Yes, so thanks for the invitation. I'm sorry I couldn't attend in person. It's a very busy time here. But I'm going to tell you about plasma wake field acceleration with the focus on our awake program. So the motivation for looking into a new kind of accelerator is basically to see if we could find a way to find more compact, less expensive colliders that can bring us to higher energy. So I think everybody in your workshop, of course, knows the projects which are being discussed for the future. So there's, for example, the existing LHC is this small ring. And if we look at then proton colliders that have been discussed for the future, there's, of course, the FCC. There's also, of course, the Chinese version. And so these are very much larger. So the energy limit for circular proton colliders is basically given by the strength of the magnetic field. So if we want to go to higher energies, and we have a limit on the strength of the magnetic fields that we can provide, then we have to make ever larger colliders. So the energy gain here relies primarily on magnet development. And of course, then there's a large effort, very significant effort underway to try to improve the strength of the magnets. If we want to go to a collider which basically collides point-like particles, as far as we know, electrons, muons, so the leptons, of course, this is preferred in many ways because then we're colliding simpler objects than the protons. But there, because of the radiation problem, so the power radiated is proportional to the gamma factor to the fourth power. If we try to go into a circular accelerator, we have to build a linear accelerator to get to the very highest energies. And so this means very, very long accelerator complexes. So this makes things also, of course, then difficult and expensive. So this is why we think about using a plasma. And the plasma is a collection of free positive and negative charges. And the reason we want to think about using a plasma is we can sustain very high electric fields in a plasma. So the idea is if we have a plasma, then we can imagine sending an intense particle beam or an intense laser beam through the plasma. So here's in this picture, you can see here, there's something called a drive pulse. This could be a compact beam bunch of electrons, for example, or a compact or a laser, short laser pulse. And the effect is to drive the plasma electrons outwards if you have an electric field pointing radially out. And these electrons then start to move in the plasma. So maybe I should say, first of all, in the zeroth approximation, the ions we think are very much heavier than the electrons. And during the time of this interaction, we think of the ions as basically stationary. So the only thing moving in the plasma are the electrons. So we have our drive pulse, and it starts the electrons moving. Here, of course, there's a 2D picture, but the fields here are radial. So the electrons are pushed out radially. This drive pulse is very short. So and it's moving with the speed of light in this direction. So after it's passed, then what's left behind is a positive column of the ions, which we say are immobile. So the electrons see this positive column left behind, and then they come back on axis. So if we think back here, these are the electrons which are coming back on axis after our drive pulses move. So basically the electrons are undergoing some kind of simple harmonic motion across the axis, and depending on the phase, you get this kind of bubble structure in the plasma. And now the idea is to put your particles that you want to accelerate, let's say another bunch of electrons, in this location. And in this location, you have a very strong electric field because of the overdensity of the plasma electrons, which are located here. So this is the basic idea. And in fact, the physics, at least in this zeroth approximation, is quite simple. So the frequency at which our plasma electrons are oscillating is given by this expression, and it depends basically on just fundamental parameters, the charge and mass of the electron, and on the square root, when we take the square root of this square of the angular frequency here, so on the square root of the plasma density. So to get some numbers in here, we can think, so if we have, imagine our whole structure is moving with the speed of light, we can calculate a wavelength given this frequency. And this wavelength for a plasma density of 10 to the 15 free electrons per cubic centimeter is 1 millimeter. Okay, so we make little 1 millimeter structures. They could be smaller if we have a higher plasma density. So this is basically how this is scaling. Okay, so the idea here is not so new. In fact, it dates back to Tajima and Dawson. And so it's from 1979. And they were imagining what at the time seemed like really science fiction, lasers that produce 10 to the 18 watts per centimeter squared, and would then be able to produce electric fields at the level of 100 gigavolts per meter. So this is more than 3 orders of magnitude higher than what we have today in our particle accelerators. So this is what made this idea look very exciting. So the original idea was for lasers as a driver here, but then particle beams as drivers were also introduced very soon thereafter by Pizin Chen. And basically, if we have a compact charged particle beam, then again, the fields are just transverse in our frame when the particles are moving by the speed of light. So basically, the physics is the same. So this is how, in principle, the plasma acceleration works. And why? Okay. So now the question is, what is the right way to do it? What kind of driver do we want to actually use to build our plasma accelerator? And so here we have different choices. So the point is, if we're thinking about a high energy collider, normally we'd like to really collide bunches of particles. And so here we have to look at the energy content of the bunch of particles. So imagine we have 10 to the 10 particles at 1 TeV. Then in one bunch of these 10 to 10 particles, the energy content is a few kilojoules. So we're going to have to conserve energy. So whatever energy is in the driver, that's the maximum energy that we can transfer to this bunch of particles that we're accelerating. So these lasers, which now today reach these very high power levels, 10 to the 18 and more watts per centimeter squared, they achieve it primarily by producing a very short pulse. And if we look and see how much energy is actually in that laser pulse, then it's at the level of tens of joules typically for the state-of-the-art lasers. So it's actually quite far from the few kilojoules that we would need. If we look at existing electron beams, for example, the facet beam at SLAC, that has 30 joules in one bunch of electrons. Again, very far from the few kilojoules. So if we want to realize a plasma accelerator based on either lasers or electron bunches, you would have to have a staged system. So that's what these drawings here describe. So here from Wim Leemans and Eric Esseré from in Physics Today, they described what a staged laser plasma accelerator might look like. So you would have the two wings, let's say for an E+ E- collider. Each stage would provide about 10 GeV of acceleration, and you would have 100 of these stages to get to the TeV level. So although the acceleration is very, very strong inside these plasma regions, let's say 100 gigavolts per meter, you lose effectively a lot of the strength or the average strength because of the gaps in between these cells. And you have to sort out how you're going to extract electrons out of one plasma cell and re-inject them into the next. It's the same thing for the electron-driven plasma accelerator. So here's a kind of layout put together by Eric Adli. And again, it's many, many stages of acceleration so that you can reach the TeV scale. So this complexity of having to have many stages, basically due to the limited energy in these drivers, led us to think about using protons to drive the plasma wake. And the reason is, if we take a bunch of protons from the SPS at CERN, that's already 20 kilojoules, LHC bunches of protons, 300 kilojoules. So in principle, we could accelerate, at least based on the energy budget, our electrons, one bunch, 10 to the 10 particles, say, to TeV with one bunch of protons. And so we wouldn't need all of this staging. So we did some calculations, and indeed, we showed that, at least, of course, in simulation, with one LHC-driven stage, we could produce 5 or 6 TeV electron bunches. And so this, in principle, can work. Okay, so one of the questions might be dephasing. So, of course, protons are much heavier than electrons. And so you might think, the electron will outrun my proton at some point. Well, it's true, it does happen, but this goes like 1 over the gamma factor squared. And so with the SPS, this dephasing problem, basically electrons catching up with protons, only happens after about 100 meters. At the LHC, it takes many kilometers. Basically, you see it here. And with the FCC, if it were to exist, would be really much, much longer. We don't have to worry about it at all. Okay, so what are the problems? What are the issues if we want to use protons to drive our plasma wake? So I mentioned that the driver has to be very short. And the reason is that we want to produce these very basically radially outward electric fields. So we need our electric fields to go radially outwards. Oops. And they should also be compact. So if we have a long bunch, then, so here's from Feynman's board explaining, of course, how the electric fields look transverse to us when we have a fast-moving charge coming by. Imagine you have a long bunch, then these radial electric fields would be produced over a long distance in this direction, and this would then destroy this plasma wave that you're trying to produce. So we need to have it compact. In fact, here's a kind of an engineering formula, which you can see that the maximum electric field that we'll be able to produce in the longitudinal direction by compressing or having our plasma electrons come back on axis goes like 1 over the length of our bunch. This driver here, this is in this case where this sigma z is the pulse that's driving this plasma wave. It goes like 1 over this distance to the square. And today's proton beams or bunches have very sizable distances, like tens of centimeters or 10 centimeters. I think at the LHC something like 8 centimeters. And so basically this is a huge reduction factor and we don't get very strong electric fields. So we need to find a way somehow to have very compact, compressed longitudinally proton bunches. So this is the main limitation. I mentioned the dephasing aspect. So the electrons, at some point, if we're accelerating electrons with our proton driver, the electrons will start to outrun the protons. That means they'll move away from this strongly accelerating phase into a phase where actually they get defocused and we would lose the electrons. So, but as I also said, this dephasing goes like 1 over gamma factor squared. So at very high energies where gamma is large, this doesn't cause a significant problem. Normally in our accelerators, of course, we try to accelerate in vacuum, and because we don't want the particle interaction. So you might wonder, if I'm trying to do acceleration in plasma, isn't this going to scatter away all my particles? And of course, this is an issue, but we can calculate the interaction length. And I mentioned the plasma density, and this is at the level that we would be interested in, for example, for our proton-driven plasma acceleration. With these densities, it's actually a pretty decent vacuum. So it's not a high density of particles, and the interaction length is actually quite long. It's more than 1,000 kilometers. So this allows us to really accelerate over significant distances before we lose too many particles through particle interactions. So really the fundamental issue here is the length of the proton bunch. And the question is, can we squeeze the protons together in the longitudinal direction so that we can have significant wake fields? So here nature really saved us. And in fact, the plasma interaction is what saves us here. So what happens is that if we send a long bunch of protons into a plasma, then there is a natural interaction between this long bunch and the protons, which modulates the proton bunch. This was first discussed in this seminal paper by these authors about 10 years ago, 12 years ago. And this is the so-called transverse two-stream instability. And here I have a little movie. What happens? So you imagine here in the yellow-orange color, these are individual protons in a bunch. So this is here half of a long proton bunch, and it's traveling through the plasma. Oops. And as it does so, then you notice that some of the protons get pinched towards the axis, and some of the protons get kicked outwards radially. And the pattern develops. We call these little segments of the proton bunch here micro bunches. And these micro bunches are spaced at exactly this plasma wavelength, which I mentioned. So what this allows is then, in fact, these micro bunches will act coherently to increase the plasma wave that we're creating. So instead of having one driver, which is driving our plasma wake field, we have a large number of smaller drivers, each acting coherently to drive this plasma wake. And we found in our calculations that indeed, with this kind of approach, we can generate fields which are effectively as strong as if we had started with one single bunch driving the wake field. So this is what, in fact, allows us to use the proton bunches also as drivers of our plasma wake field, although these proton bunches, you might think, are much too long to drive significant plasma wake. So this is our approach, and here summarized. So one of the keys is that we need to be able to control the timing of this modulation process, because we're going to want to inject some electrons into this plasma wake field that we've created. And we have to inject the electrons at just the right place so that they're feeling the strong accelerating fields and are not in some different location where they might get kicked out. So in order to create this, this timing, we have to seed, what we call seed this modulation process. And we do this with a short laser pulse. So we have here in this picture, the protons are in red, and they're traveling through the plasma. There's a short laser pulse, which starts this modulation process. And then this builds up this strong plasma wake, and now we can accelerate our electrons with a timing which is defined relative to the short laser pulse. So this is the scheme that we developed. So this all looked quite promising. So we decided to build up collaboration and try this out. So here's our very first meeting. Frank, which I think is in your meeting, is also in this picture and part of our initial discussions. So we discussed all of this, these ideas. It looked nice. In 2013, we submitted a design report. It was approved, and in 3 years, basically, was the time it took us to build up the experiment, and our program started in 2016. So we have now this awake collaboration to carry out this this plasma wake field acceleration based on a proton driver, and we're up to 22 institutes. Of course, it's maybe a little misleading because many of the institutes here are just a couple of people. So the actual active number of people in the collaboration is more like 50, but it's still, I think, a strong collaboration, and we're making good progress. So that's our collaboration. The experiment, since we're using protons, takes place at CERN, and we need the CERN beams. So here's the CERN accelerator complex. You see the different stages in blue here. This ring is the SPS, and there's this beam line which was already existing before we started. It was the CERN Neutrinos de Gran Sasso, CNGS facility, and this program sending the neutrinos to CERN to Gran Sasso ended in 2012. So this site became available for us. So we installed our experiment in this beam line. So basically here, so just ahead of the dump, so-called beam, or the target where the protons were used to generate pions and then neutrinos. So this is our location. This is what the layout looks like. So down here, this is a 750 meter long proton beam lines I said already existed before, so we didn't have to come up with the money to build this ourselves. It was already there. So this is the proton beam line leading to this target, which was used to produce the neutrinos for CNGS. In this drawing, the protons are coming this way. Here in orange is our plasma cell. Here is a wall behind which was the target, which is highly radioactive to make the neutrinos for Gran Sasso. We have here a couple of things. So there's an electron source, which we'll discuss, and there's also a laser. So here's the laser room. And as I mentioned, we need the laser to create the plasma and seed this modulation. Okay, so the heart of our experiment is the plasma, and the plasma source is something that we designed and had built from our Max Planck Institute for Physics. It's based on a rubidium vapor. So we heat up some rubidium, create a rubidium vapor, and then ionize this rubidium vapor with a laser, and in this way create our plasma. Rubidium is very good because of the very low ionization energy of that electron. And so what we can do is we can measure the rubidium vapor density very accurately, and then singly ionize every rubidium atom along the path of the laser, and then we have a very well-defined plasma density. So this is a key for us to have a very well-controlled plasma density. In fact, we think we know that we measure the plasma density at the 0.2% level, which is actually quite impressive for plasma physics. So we had our first run in 2016. So maybe amazingly enough, in this day and age, our experiment was setup was on time, on budget, and we had everything built and got started. We had in 2016 basically 4 days of running. That's it, and the first 3 days nothing worked. But on the fourth day at 5 in the morning, finally we got some nice data, and so everybody was very happy. So this was I think a very successful start to our experiment. So what did we see in what we call run one? So run one was 2016 to 2018. And our goal in run one, there were a couple of goals. One was to look at this modulation process of the protons. So what you see here, this is now real data. We have a device called a street camera, which allows us to really measure in time the passage of particles, so we can measure the longitudinal profile of our proton bunch. And so here in the top image is without plasma, what our proton bunch looks like. And it's a very nice, basically Gaussian distribution of protons along the bunch. And then, so in this picture, the protons are moving towards the left. And then we turn on the plasma, and we have the seed basically in this location, which starts the modulation process, and you see the formation of these micro bunches. And we can do this for many events at a time and stack them up. And you see that basically these micro bunches always line up at the same place. And this is what tells us that we, in fact, control the timing of this process. And so we can know when to inject our electrons that we want to accelerate. So this was a very successful start to our experimental program, demonstrating that we can create these micro bunches out of a long proton bunch. We then studied whether the behavior of this microbunching was what we expected. This slide, I think, is too technical, but basically there was a predicted modulation frequency, which I showed you at the very beginning, should go like the square root of the plasma density. Here's the plasma density on this axis. Here's the modulation frequency. The curves are what we expected. The dots are the data, and basically we're exactly where we expect it to be in terms of this modulation frequency. So this looks like it works very well. We then, as part of our run one, also wanted to test the acceleration of electrons. So we introduced an electron beamline. And so here's this electron beamline that we used to inject electrons in our plasma. So we injected electrons in this modulated proton bunch and saw the acceleration of these electrons. So here's the energy on this right-hand plot, the energy that was gained by the electrons as a function of the plasma density on this axis. And we basically expected to see about 2 GeV energy gain, and this is in fact exactly what we saw. So the electron acceleration in the proton-driven plasma wave field works, and it can work with today's existing proton bunches. So this was a very nice success. So where are we today? So we had our so-called run one, 2016 to 2018. We then proposed a run two for the CERN, and it was approved. So our run two started last year. And our goal in run two is to demonstrate that we can really have a stable acceleration of a bunch of electrons with these high gradients over long distances, and that we have good properties of this electron bunch at the end of this acceleration process, which means a good emittance, so that the electrons are really, reasonably compact in phase space, so we can handle them later on. So we see 4 phases to what we call run 2. The seeding of the self-modulation process. In this case, we're also trying it out with electron bunches, the seeding, rather than with lasers for a technical reason, which I won't have time to get into. We want to introduce a different kind of plasma cell. The reason is that we want to freeze the modulation process of the proton bunch before we destroy the whole proton bunch. So this is a key. And then we want to inject electrons and accelerate over long distances without emittance blow up. And for this, we're going to also have to introduce scalable plasma cell technology. So we're going to need plasmas that can reach tens or hundreds of meters. And so we need to have the right scale, the right kind of plasma technology for that. So those are the goals for run 2. We started with this run 2A, this electron seeding of the modulations last year. And just to look at here a flash of the results, lining up many events, we see, so the event numbers here, this is the timing of the micro bunches, and this looks very good. So our electron seeding of the Wakefield process is fine. So run 2A, so this first point here, which is 2A, is comes with a check mark. This was realized. Run 2B, which is starting next year. This point, the main point of this run 2B is to have this density step in the plasma. This will allow us to freeze the modulation process. This is the result which we studied and understood was necessary to really maintain the gradients, these accelerating gradients at the GeV per meter level over long distances. So we've designed and now also prototyped this new kind of plasma cell. It meets specifications. It's being built now and will be installed early next year. And we'll start our run 2B next year with this new plasma cell. Then down the road, we want to really inject a compact bunch of electrons that can then maintain its emittance during the acceleration process. For this, we understood that we need a different kind of electron injector, which can produce electrons of higher energy, here about 100, 150 MeV. And the reason is that this compact electron bunch can create its own little bubble in the plasma, and inside this plasma bubble, it then can preserve, the emittance will be preserved, and we can accelerate over long distances without this electron bunch blowing up. So this is for run 2C, which will come after the next long shutdown of the LHC. So maybe 2027, 2028, somewhere around there. And then run 2D, we want to introduce a new plasma cell technology, which can allow us to have plasma cells which stretch out over very long distances, so we can accelerate to very high energies. So there are 2 different technologies which we're pursuing on the plasma cell. One is so-called helicon plasma, which is something that's used in the plasma physics community. It has a solenoidal magnetic field, which is used to contain a plasma, and the plasma is heated with the RF power. So this is under study. The Max Planck Institute for Plasma Physics in Greifswald has built a prototype, and this is coming along nicely. And a second option, which would be much less expensive if we can get it to work, is just a discharge plasma. So here, there's a lab set up at CERN. Apologies for that. So there's a lab set up at CERN, and a group from Lisbon and the Imperial College in the UK are developing this discharge plasma cell. And we're going to also try this out next year with a 10-meter plasma cell. Here you see the light produced, and it looks very uniform. So this also looks like an interesting technology for the future. Okay, so let me wrap up just to tell you what we think we could achieve in terms of particle physics applications with our scheme of proton-driven plasma wakefield acceleration. So since we rely on the protons, we first have to accelerate the proton bunches to high energy, and then we inject these proton bunches into our plasma. This will mean it will be very difficult to achieve high luminosities. So the main, really the physics that we have to think about is what can we do with basically high energy electron bunches. And so one can think of beam dump or fixed target experiments. So search for dark photons in a beam dump experiment, or fixed target experiments in a new energy regime. Or we can imagine looking at physics processes in a collider where the cross sections are very large. So I'm talking about QCD. So looking at QCD processes, for example, an electron-proton, electron-ion collider. And so here, although we would have low luminosity, we would be in a very different energy range. And so we've done some studies here, and we can see, for example, we could extend the kinematic range from Hera by a factor of 100 or several hundred. And so this could allow us to introduce and enter into very new regimes of QCD. So this could be very interesting. And then, of course, there are all the things that we haven't thought about yet, like maybe applications for muon colliders and these kinds of experiments. So I think we've just started to evaluate the particle physics potential. We've been focusing primarily on developing this technology and showing that it works. I think we're well underway, and the ideas will come on how to use it. So as a summary, we've now had 2 runs in Awake. Our goals for run 1 were completely reached. We're in the middle of our run 2. In fact, run 2A, second half, is just coming to an end this year. And then next year, we start with our run 2B. And I think we have very nice long-term prospects. It's very exciting. And so stay tuned for the next few years. Okay, that's it from my side.
Thank you very much. It was a very nice talk, and we are open for questions. So let me start by asking a question myself while the audience gathers thoughts. So how would you actually go about engineering a collision in such a system? Because I mean, it's if you wanted to do a kind of a beam collision experiment, the way the technology is being constructed right now, you have essentially in a wake field you produce a certain beamed geometry, but how would you get the 2 beams to actually, collide?
Yes, so we started thinking about that. So good question, thanks. So yes, so the acceleration takes place in the plasma, and then the bunch comes out of the plasma and has to be handled and transported in some way. So there's actually one of our postdocs has just put together a paper with a team on showing how you could transport this bunch of high energy electrons that was accelerated in the plasma to some downstream location. So it's not happening in the plasma. The accelerated bunch of particles is extracted from the plasma and then transported with some, let's call it transport and focus line to the region where you want to do the collisions.
Just to add to that, do you see a deceleration when you get out of the plasma, or that's not a problem?
No, it's not a problem. The issue that we're actually looking at in some detail is whether there's an emittance blow up when we come out of the plasma. So this I think would certainly happen at low energies, because there are always changing fields, let's say, as you extract from the plasma. You can't go from these very strong fields to zero field in no distance. So there's a gradient, and when you traverse this gradient, then they can produce some transverse deflecting forces, which then blow up your beam. But our studies indicate that when we're at very high energies, these will not have a significant impact. So I have to point out that we're not aiming for ultra low emittances here, which might be wanted for, let's say, electron-positron collider. So as I mentioned, we know that that we have to aim for lower luminosity applications. So if it's a fixed target or a beam dump experiment, then the emittances that we're aiming for maybe, I don't know if these units mean very much to people in your audience, but let's say 10 millimeter milliradians. And this can be achieved despite these deflecting forces coming out of the plasma. If we want to have a collider where we collide our electron bunches with a proton bunch, then in any case, our luminosity will be set by the size of the proton bunch. The proton bunches, the transverse sizes are much, much bigger than what's being discussed for E+ E- colliders. So we think that we won't have, it wouldn't be an issue to match the size of a proton bunch. So I think the main issue is really not any deceleration of the electron bunch, but a kind of a emittance blow up with transverse deflections at the plasma exit. But I think at high energies also will not be a problem.
So I take over where you left. So this luminosity that which we all of us in Collider experiment are really, sort of one of the main figure of merit. So what are the, like you said, currently it's not feasible to have an electron positron, sort of with a decent luminosity, but electron proton part probably that is okay. But what are the sort of thoughts looking ahead that how to further squeeze the emittance, or how to increase the luminosity? I mean, whether you work on the numerator of the expression, master equation, or the denominator. So what are the thoughts looking forward? Because luminosity will be really one of the key things.
So yes, so there are my thoughts, and then there may be thoughts of other people. So as you say, if we go to higher energies, then our cross sections go like 1/10 of mass energy squared, and so then we say our luminosity should also scale with the center of mass energy squared as we go up in energy. That's a hopeless game, I think. That's my sense. So really trying to imagine, I don't know, pick a number, 100 TeV E+ E- collider with luminosities of 10 to the 35, 10 to the 36. I don't want to look at the power bill there. That's just going to be really out of it. So I think my approach to this is to say, maybe we have, as particle physicists, we need to think of what else we can measure, and maybe be a little bit more creative. Personally, I think there's still a lot to be done in QCD physics, high density physics, collective effects. We don't understand very much about QCD. What we understand is in the perturbative regime, a tiny little bit of what QCD is telling us. There's a lot more there. So I think it's going to be very hard to really solve this problem of very high energy, very high luminosity colliders. And maybe what we should be thinking about is other things that we want to learn as particle physicists. And then these tools that we're talking about, like this proton-driven plasma accelerator, can produce very high energies, but not necessarily in the collider mode, E+ E-, but in these other configurations. So I don't have a solution, if that's what you were looking for. I don't have a solution on how we get to a very high energy, high luminosity collider. And my message is also to all our theory friends, maybe we should look beyond just the collider and ever higher energies and smaller distances and think of other kinds of physics we want to do.
Right. One last question.
Yeah, my question relates to the driver. You mentioned that the laser is about 1,000 times less efficient than a proton driver. Now, is there any hope on the laser or maybe a maser front that you might be able to do it that way with advances in technology?
Yes, yeah. So thanks. Normally, I do talk a little bit about the developments on the laser front. So today's lasers are, let's say, standard titanium sapphire lasers working with this chirp pulse amplification. It works beautifully, but it's going to be very hard to get an efficient, so high rate, high energy pulse from that kind of laser. Again, if we just to connect back to our previous discussion, I mean, these lasers have at sub% level efficiency to get energy out of the wall plug into your laser. So again, this would be horribly expensive to try to do things this way. However, there are, I think, very exciting developments in using, for example, fiber lasers. Fiber lasers can be very high rate and very high efficiency in terms of how much energy you get out of your wall plug into your laser pulse. But they're low energy per fiber laser. So what people are working on is trying to put together arrays of these fiber lasers and phase them correctly. And the dream would be something like 10,000 fiber lasers all synchronized so that you can add their pulses together to produce one very high energy, also very high rate laser pulse that you could use as your driver. I think if there's going to be a hope for something like an E+ E- collider based on plasma technologies, it would be in the end using that kind of technology. So that would allow high rate and efficient and high energy laser pulses. But that's still a development that's underway, and we'll have to see how far they get with that. But it is promising, I agree, yes.
Great. So thank you very much. And we move to our next speaker. That's Michael Dozer from CERN. And he is going to talk about quantum technologies for high energy physics. And Michael, you'll have your 40 minutes. We'll just have to leak into lunch. Okay.
Go back. Yeah, there we go.
Yeah.
Okay. Thank you very much. I will try to be quick on some things and maybe skip a few topics at the end if time runs short. But basically what I'd like to do is talk about quantum technology for high energy physics, whereby high energy physics is anything that is done at places like CERN. So I also include low energy particle physics there. I'd like to say a few words on the landscape, what we're talking about in terms of the terms, what I mean with quantum sensors, then talk about quantum sensors for low energy particle physics experiments or measurements, for new particle physics experiments, before coming to applications of quantum sensors to high energy physics experiments. So first of all, just a very quick clarification. For me, this is what I'm going to be using as the terminology. Quantum sensors are things that registers change of quantum state caused by the interaction with an external system. So I'm talking about transitions between superconducting and normal conducting, or transitions of an atom from one state to another, or a change of a resonant frequency in a system in a quantized manner. So in that understanding, a quantum sensor is a device, the measurement capabilities of which are enabled by our ability to manipulate and read out its quantum states. Very simple description, which immediately tells you that this is useless for high energy physics because, unsurprisingly, quantum sensors are ideally matched to low energy particle physics. These are very low energy transitions. But I will nevertheless show that although one would expect this to be useless, there are definitely areas in high energy particle physics that will benefit. The area I will not cover at all is entanglement. I haven't found any way to use entanglement for high energy physics detectors, which means that somebody else has to come up with creative ideas. And I'm sure there are ways to use entanglement, but I will not be talking about that. So we're talking about technologies in these realms here. I've numbered them 1 to 6 because this is actually part of the ECFA detector R&D roadmap, where we have 6 different families of quantum systems or quantum technologies that we're using and looking at the impact on high energy physics or other particle physics experiments of. Superconducting devices, and this includes also cryoelectronics, so transition edge sensors, superconducting nanowires. Then spin-based systems, nitrogen vacancy diamonds, for example, optical clocks, ionic, atomic, molecular systems, optomechanical sensors, and metamaterials. Anything where you do quantum engineering at the nanometer scale, including 0, 1, 2-dimensional materials. And the idea is to see where these kinds of families of sensors can allow one to study these domains of physics, so searching for new physics beyond the standard model, searching for dark matter in different ways or in different incarnations, tests of quantum mechanics itself, and searches for symmetries and breaking of symmetries, for example, electric dipole moment searches or tests of fundamental symmetries. So this is basically what I will be talking about. Oh, thank you. Zoom has stopped due to attempted, okay, let's see if I can ask it to, it does not want to let me switch over, so I think I need technical help. But it says stop share. It's still sharing. So now you are sharing? Okay. Hmm? See, this is why I like the video connection. It just works. Sorry, go ahead. Well, now I need to. Okay.
Yeah, it does. Just
Okay. All right. So the parts that require R&D, and you can see the intensity and the size of the dots, indicates that if you want to use quantum sensors for high energy physics detectors on a time scale of the next 10 years or so, you're basically going to have to do a lot of R&D on the sensors themselves. This is okay. And there's a good overlap with other chapters of this detector R&D, for example, particle identification and photon detectors, where also technologies like metamaterials and photonic crystals are being looked into. Why is this frame showing up? So there's also an overlap between the developments of the detector R&D roadmap and the activities of the Physics Beyond Collider at CERN, which really focuses on low energy particle physics, where one looks at expanding the initial experiments that have been using quantum sensors worldwide to trying to scale these up, and then using systems like particles, atoms, ions, and nuclei, radio frequency cavities, or atom interferometers to look for physics beyond the standard model. And I'd like to start out with talking about particles, atoms, ions, and nuclei as systems with which one can test QED, time invariance violation, parity, Lorentz invariance violation, or dark matter searches. And here there are several systems that are very nice to play with, in particular, highly charged ions in penning traps, where many of the effects scale very nicely with the charge of the nucleus. This scaling of the charge with the charge means that transitions that are in the microwave regime, for example, the hyperfine splitting in boron, in the case of argon 13+, are shifted into the optical regime, which means that one can use the very high resolution optical techniques to probe for shifts that would be caused by beyond the standard model interactions at a very, very high sensitivity. This kind of system also allows looking for electric dipole moments in molecules, studying nuclear clocks, for example, thorium-229, or molecular and ionic clocks. And these systems are being worked on at CERN in some cases. The system I'd like to focus on first, or just mention rapidly, is antiprotonic atoms, with which one should be able to produce and study novel, highly charged ions. For example, by using the simple capture by an atom of an antiproton, which then cascades down, completely strips away all the electrons, annihilates at the surface, and where the remnant nucleus, the completely stripped nucleus, can then be combined, for example, with a positronium atom or a protonium atom to go far beyond what is currently the standard highly charged ions, which is a nucleus with a few remnant electrons, to instead have systems where one has a hydrogen-like system with a highly charged nucleus and a single electron in a Rydberg orbit, or a single antiproton in a Rydberg orbit. And this is a very nice, clean system, very easy to calculate, and highly sensitive. One can also go beyond that and look for exotic couplings by replacing an electron in a Rydberg atom with an antiproton, or then trying to use these antiprotonic Rydberg atoms, an analog of the system here, in molecular states, whereby one would replace one of the electrons in a Rydberg system by an antiproton, and then end up with antiprotonic atoms in a Rydberg state, which would allow one then to look for things like an antiproton EDM, similar to the electron EDM in molecules. Switching gears to axions or dark matter searches, the windows that are normally explored are here in blue around a microelectron volt, and of course, indirect searches at HEP, high energy physics experiments. One would like to cover a much wider range, especially towards the low mass region. And here, one of the problems that one faces is that the figure of merit goes, of course, with the coupling and the mass of the axion squared, but with the fourth power of the magnetic field, the volume squared, the inverse square of the temperature, and the quality factor of the RF cavities. So these are all parameters that one would like to maximize, and some of these are incompatible. In order to get into this area here, one needs to use some tricks. And for example, the base experiment has been using a basically an LC circuit to look at antiproton spin flips inside a penning trap. This LC circuit is actually a detector in its own right, and one can use the noise spectrum of this whole system, that's this distribution here, to look for perturbations that would be induced by an axion interacting with the magnetic field here, the nice thing about their experiment is that they need to work at extremely low temperatures. So they need the lowest temperature LC resonant detectors ever built, which have a very low effective temperature here, and also a very high quality factor in their case, which means that they can use the non-observation of a peak in this spectrum, in this noise spectrum, to exclude a mass region, which on this plot here looks very large because the scale is very small, but on the more usual scale of 10 to the minus 4 to 10 to the minus 11 electron volts is actually just this thin blue needle. So it's a very, very narrow region that is excluded, but this is just a first measurement. By expanding the system using superconducting tunable capacitors, so for this part here, and laser-cooled resonators, as well as a stronger magnet, this system will allow them to expand their search from this narrow spike to this whole blue region here, which shows that even a creative use of a completely different system, like trying to look for CPT violations by measuring the magnetic moment of the antiproton and comparing it with that of the proton, allow one to look for dark matter candidates. And in fact, the same approach is also visible here. In order to cover the region that goes below about 10 to the minus 6 electron volts, one needs to address very low mass axions, which means basically very strong magnetic fields, huge volumes, and so on, or building heterodyne cavities, whereby one has two resonant frequencies, the difference of which corresponds to the sensitivity of the axion mass. And having cavities like this is a way to try to cover very small axion masses by modifying the value, the precise value of the two resonant frequencies, or rather their shift. And appropriately designed resonant cavities can go down to very, very low masses this way, as long as one can maintain both the magnetic field strength and the quality factor. And this is in fact the challenge that is being addressed, for example, at CERN, by building superconducting cavity coatings that are able to maintain their high quality factor of 10 to the 5 or so, down to up to very, very strong magnetic fields of several Tesla. I won't talk about atom interferometers because we already had two presentations, or actually Oliver gave his presentation, and John is an equally knowledgeable representative of this, just to point out that also these kinds of experiments are being contemplated, being carried out at CERN using the infrastructure of CERN. While not contributing to the quantum sensing side of things, CERN would contribute, or particle physics would contribute, infrastructure to enable this kind of slow growth from meter scales to 10 meter scales to 100 meter scales to then large scale interferometers in space. So since I do not want to spend too much time on the low energy particle physics side, on the high energy particle physics side, I'd like to now focus on how one can use quantum sensors for high energy physics detectors. And really, I should say that the following is going to present a handful of ideas that rely on quantum devices or are inspired by them, but that don't necessarily use them as quantum detectors per se. So one uses their functionality, but not the fact that they're extremely sensitive. The main focus here is on tracking, on calorimetry, on timing, on novel observables, on pileup, dealing with pileup. And much of this is closely related to nanostructured materials, especially the engineering type, aspects. And there's a paper that I would like to refer you to, which covers a few more of these ideas, which are not fully developed concepts. These are just approaches that one might contemplate to try to build detectors. And all of the following is very speculative. So in other words, please don't shoot the messenger, but rather try to see this as an encouragement to think how these systems could be used. So I'll cover four categories. The first one is the most obvious one, the metamaterials and low dimensional materials, such as quantum dots and nanolayers. But I'll also indicate how one might be able to use atomic manipulation to build new types of TPCs or enhance the functionality of TPCs, how one might be able to manipulate detectors or scattering processes that would lead to something like a helicity detector to measure the helicity of a particle. And finally, how one might use superconducting sensors also in high-energy physics experiments to look for physics beyond the standard model. So the first one is quantum dots. Quantum dots are nanometer-sized structures that have a very nice property in that the emission spectrum of these dots depends on their size. The largest ones emit in the red, in the infrared. The smallest ones emit in the blue. And you can see here a nice example of different nanodots suspended in a liquid and illuminated and brought to fluorescence. And this means that one has chromatic tunability, which means that if one can coat a scintillator with these dots, one can try to optimize the quantum efficiency of the scintillator to that of the photodetector, which means you basically have a fast optimizable wavelength shifter. And you can move from the UV to the visible light. Now, of course, coating this on the surface of a scintillator is maybe not very interesting. What you'd really like to do is embed it in high Z material and make the scintillator itself emit not in the UV, but actually be a scintillating wavelength shifter hybrid. Combining the nanodots with maybe microcrystals, because it's probably not going to be easy to embed nanodots inside a melt. But instead, maybe embed them in a polymer matrix, which means you would have a quasi-continuous visible light emitter. And then, of course, you have to think about how this light might be reabsorbed, which brings me to the next topic, quantum calorimetry. So imagine you have this seeding of the crystal with nanodots emitting at not one specific wavelength, but at different wavelengths, as in here. These nanodots have very sharp emission spectra. The emission spectrum itself is about 20 nanometers wide for all of these different colors. And the absorption spectrum is well separated from 472 nanometers emission spectrum here to 460 absorption spectrum, which means that if I have a narrowband emission spectrum and I can only absorb at longer wavelengths and I have very rapid decay times, I can, through the choice of these particular nanodots, build something like this, in which I embed in different slices of a calorimeter, different nanodots, the first of which emit in the infrared or red. This red light is not absorbed by the slab itself, but a priori, it's not going to be absorbed by the following slabs either. The same thing for these, the same thing for these. And the more of these narrow band emitters you have, the finer grain the axial distribution will be, which means that you should be able, by measuring the spectral intensity at the output of the scintillator, obtain information on where the light was formed, and in other words, obtain information on the shower profile of the calorimeter. So this is just a standard calorimeter. Right now you have a photodetector that just measures the integral. You just have to replace the spectrometer here by, the photodetector here by a spectrometer. And for that, you might think of using something like meta lenses, which allow you to build in a very thin layer a spectrally dispersive lens that you would then have several photodetectors on measure at the end. So if one can build this kind of device here and this kind of device here, one has a shower profile measurement in a calorimeter. Now, of course, one can do this in a single block. I can also think of doing this in single fibers, and then by having multiple fibers, measure the full 3D spectrum of the shower, the depth and the width of the spectrum. Now, this is just a passive scintillator. It doesn't do much more than just emit light when a particle goes through, but one can think of using quantum wells, quantum dots, quantum well dots, or quantum cascade lasers to think about the possibility of providing active scintillating material. Scintillating material that you can turn on and off, or even amplify. You could think of modulating it, you think of amplifying it, you can think of priming it before a collision happens and turning it off again afterwards, and where you could adapt the gain in situ. Now, this comes from the idea that these different structures here, solid state structures inside gallium arsenide, and where you insert structures of indium arsenide, emit, depending on the size of these structures, again at different wavelengths. So you have quantum wells emitted around 950 nanometers, quantum well dots at 1,000, and quantum dots at around 1,300 nanometers. These are very rapid emitters. They're radiation resistant. The emission is in the infrared. Now, this is both a challenge, but also a boon, because silicon is transparent at these wavelengths. So you might even be able to think about transporting this light from a scintillator positioned at the inside of the tracker rather than at the outside of the tracker through the tracker, while having the photodetectors just inside the calorimeter of an onion-type collider experiment. This is an example of what you can do if you have a well structure inside here where the electrons are up here, the holes are down here. These are the structures inside the gallium arsenide. If you apply a voltage pulse, you change the voltage here, the electrons fall into the holes go in here, you get an excitation and emission of a photon. So this is the kind of pulsing that I'm thinking of, whereby you would move electrons into photons at a time of your choosing. And if you take that one step further, imagine you now have this kind of silicon detector, which generates many electron hole pairs, coupled to a quantum cascade well, where you have a photon emitted for every transition from one step of the well to the end, to the next. So instead of having just a single electron produce many photons, here you would have many electrons, all of these produced by the ionization of a minimum ionizing particle, times the number of steps. So you get a huge number of infrared photons produced from the silicon, and where the number of photons is in addition proportional to the energy that's been deposited inside the bulk matter. Now this requires engineering, of course, at different scales, silicon detectors or gallium arsenide detectors coupled to these kinds of complex structures. And this is not a new idea. This has been discussed already in the context of the dot picks, which are single MOS transistors, which perform two functions, as a hole collecting electrode and as a channel current modulation electrode. These are extremely fast and rapid devices. Similarly here, a detector or a device made of indium arsenide, gallium arsenide scintillating material would allow, and this is not my plot, increasing both the decay time, so being very rapid, but also the photon yield, because this is actually where you want to be. You want to have very rapid photon emission, and you want to have large numbers of photons. And if you look at the standard scintillating materials, lanthanum bromide, LiSO, barium fluoride, they're all well below what already current devices of indium arsenide quantum dots, gallium arsenide devices can do. And there's potential for further growth. From the 1D material, 0D materials to the 2D materials, these are now basically sheets. So there's an activity ongoing right now in the context of the picoset micromegas detector R&D, with two goals in mind. The first one is to try to separate out the amplification region of a TPC or of a gem from the signal producing region. The problem is that the ions will drift into the amplification region and create cascades and ion backflow. If you want to suppress ion backflow, you can think of producing a gem structure which is covered by a monolayer of graphene, which will not let the ions that are produced in the drift volume into that region, but will allow the electrons to pass. In fact, in this experiment here, a test was done on looking at how electrons go through monolayers of graphene, and the transparency to electrons is absolutely excellent. So this means that if one can get graphene to cover the micron-sized gaps of a gem, then one should be able to have a monolayer filter plane between the signal region and the amplification region. Similarly, coating photodiodes, photocathodes with graphene, with single layers or few layers of graphene, allows tuning the work function of the photocathode. Here's an example. Depending on the number of layers of coating, so 1 layer of graphene, 2 layers, 3 layers, 4 layers of graphene, you can see that without the graphene and with the graphene, there's a significant difference in the work function, as long as one can control the engineering at the level of single layers of molecular sheets. let me come to atoms. You're all familiar with the TPC. Particles go through, ionize. The electrons are then drifted towards the amplification region of the TPC. And here is the separation region between the two regions, between the drift region and the amplification region. In the amplification region, the electrons are accelerated and produce showers. Now, this requires relatively high electric fields and creates backflow, as I just mentioned from in the previous slide. If it is possible to excite the atoms in the amplification region through lasers into Rydberg states, then the ionization energy that is needed is lower. You get more electrons coming out for the same number of electrons drifting in, which means that you can lower the readout, the amplification voltage, which means that you would be able to reduce the ion backflow. So this is an alternate strategy to the previous plot, whereby one would cover this part here with the monolayer of graphene. This is an atomic physics approach to the same thing, where one would basically just control the atomic physics in here, make it easier for the electrons to ionize the atoms, to release electrons. So showers would be just as potent, just as strong, but there would be less electric field, less backflow. Now, this is just in the amplification region, but if you can do that in the amplification region, you should also be able to do this in the drift region. Imagine that you're able to excite the atoms in the drift regions to a Rydberg state just before the particle collisions happen. Then these here are indicated as semi-Rydberg states. A MIP that goes through these excited atoms will release a higher number of electrons than if the atoms were not in an excited state. And so one gets a stronger signal in here, a stronger DEDX, an effective DEDX, which can then be again drifted towards the amplification region and brought down. So this would be another way to have a higher DEDX detector, have a lower electric fields, as long as one can manipulate the atoms in this region here. A different approach, a different detector. When one thinks of helicity of particles or spin, one is automatically brought to thinking about nitrogen vacancy diamonds, because these allow polarizing a volume around a single atom inside, or a single vacancy inside the nitrogen vacancy diamonds through microwaves and laser light, expanding this volume of spin polarized scattering atoms inside a very small crystal, nanometer sized crystal, and then building planes of these materials. So imagine you can do this polarization. So this is possible right now. One already can polarize a large fraction of the atoms inside a diamond. If I have such a polarized plane inside a tracker, so this is a tracking plane, this is a tracking plane, this is a tracking plane, here are polarized planes, then I will be able to do spin polarized scattering of a particle on a spin polarized target, and then through the multiple scatterings through these polarized targets, be able to reconstruct the helicity of the initial particle. One is about a factor of 100 away from being able to do this right now. The nitrogen vacancy diamond volumes, the polarized volumes, need to be increased by about a factor of 100 beyond what is currently possible. So a factor of 3 in every direction in a 3-dimensional solid is already enough to be able to get fully polarized planes. And this would be a new way, a new measurable for a charged particle inside a collider, which we currently cannot extract except through decays and partial wave analyses. The last type of detectors I wanted to talk about is superconducting detectors. For example, superconducting nanowire single photon detectors, which are normally superconducting, but when a photon interacts with this detector, it creates a short-term normal conducting volume, which then decays away again. So one gets a voltage spike corresponding to the detection of a single photon. But this doesn't have to be a single photon. This can also be a minimum ionizing particle, which means that if one thinks of superconducting nanowires not as a photon detector, but as a particle detector, it is an extremely sensitive detector. In particular, it's very sensitive to very low energy deposits. A MIP will deposit about 20 keV in 100 micron. The developments going on right now on superconducting nanowires are aiming at a sensitivity of 12 milli-electron volts per 100 micron, which means that you should be sensitive to about 1/100th of a MIP or 1/1000th of a MIP particle, which means that if you have a beam dump where you deposit the charged particles, the muons go through, you have a muon veto detector. Inside a stack of superconducting nanowires or of transition edge sensors, a particle that deposits 1/1000th of a normal MIP would still be detectable. So this is a way to look for microcharged, millicharged particles that would be produced in a beam dump. And one can use the same kind of concept to also look for very short-lived neutral particles. These superconducting nanowires, these transition edge sensors, have thicknesses of a few nanometers, tens of nanometers. And so if you have many, many stacks of these and you use them as a target, you actually have an active target that can differentiate between charged particles and neutral particles, even on the scale of tens of nanometers. So if I have a particle that is produced here in coincidence with two charged particles, and that decays then into two minimum ionizing particles, I should be able to measure lifetimes or flight distances at the tens of nanometers of scale, which is far beyond what you can do with normal vertexing. So these are just a few ideas. I don't claim that they're feasible. I don't claim that they're going to be built in the next years, but certainly it's worthwhile using these kinds of ideas to try to come up with applications of these different technologies, these different families of quantum sensors. Obviously, the metamaterials is the easiest one, but I've shown you also that atoms, spin-based sensors, also clock networks, are sensitive probes, also for high-energy physics. And the ECFA roadmap foresees starting building or working on these kinds of detectors, carrying out the R&D that is necessary to make these a reality or to show that they don't work in the next decade. So I don't want to go through this table. It will be in the slides. I think I still have 5 minutes, so I will actually go through the implementation phase, because really now we need to think about how to go from the ideas to the implementation. And this is what will happen in the next years, or actually in the next year. The idea is really to try to define a structure to implement the ECFA roadmap, in particular this Task Force 5 on quantum sensors, in form of a formal collaboration, which could be called Detector R&D 5 for Task Force 5, or RDQ, and consists of 6 families of quantum technologies. These are the families, with many different institutions, UK, Germany, France, Italy, CERN, India, indicating which particular family of quantum technologies they would be interested in working on, trying to form out of this an overall structure that would be consistent with the goals of ECFA in terms of a collaboration, but also with the goals of the CERN high-energy physics community, which is to have a small number of projects, a handful of projects, something like 4 or 5 initial projects, by the end of next year. So this is a timeline. We're here right now, finding the interested parties. We're approaching them as I'm doing right here. Try to sort of filter out a few of the ideas that would be most promising in a workshop in spring of next year. Prepare a letter of interest to be submitted to the DRDC, the Detector R&D Committee that is currently being set up at CERN and will be set up by summer of next year. Before then, refining these ideas and putting them into the form of a proposal, and then submitting them formally to the DRDC. So this is just those handful of projects that have a really significant potential, but with a focus on high energy physics. The 6 families, having them all in one place is probably going to be too difficult, because I hope that this will be a very attractive setup all over the world. The 6 families will be spread around Europe, but of course there are activities worldwide going on in HEP-related quantum technologies in Fermilab, Oak Ridge, KEK, and of course also here in India. And so we have here a hybrid structure with families being hosted in Europe, but research being carried out worldwide. And for me, the best way to combine these two activities is to use a structure for the collaboration that is similar to the structure of the FCC with a steering committee or a collaboration steering committee, a collaboration board, scientific advisory committees, and then individual work packages. So the structure I'm proposing is to have the RDQ collaboration being formed by a collaboration board, but also with active involvement of an international advisory committee, with 6 platforms, each family being hosted in a different lab across the different ECFA member states, and each platform consisting of projects that have both work packages, so really the projects that are being considered as valid for submission in the proposal to the DRDC, and additional projects. And who works on these individual projects is distributed across the network depending on the interests and the activities of each individual group. So in the end, when we'll have 4 or 5 work packages, but a large number of projects, and for each project, one can then expect that the collaborating institutes will help follow up on these projects. And for this, I would like to propose that the body that is formed of the platform collaborators, so all the institutes, the representatives of the hosting institutes and the International Advisory Committee form part of a project evaluation board, whereby any project that any institute thinks is interesting in the overall context of the ECFA detector roadmap can be evaluated. The initial projects are submitted to the DRDC. These other projects, these new RDQ projects, are internally evaluated. The benefit to the participants of this internal evaluation is that they can take this internal evaluation and then communicate to their funding agencies that these RDQ projects, which are not the same as the work packages, have been vetted by an international community of experts around the world and found to be both interesting topics in their own right, but also matching the overall goals of the ECFA roadmap for detector R&D. So one has sort of already some kind of stamp of approval, which makes the interaction with the funding agencies perhaps a little bit easier than otherwise would be the case. And I think with that, I am finished.
So we have time for a couple of quick questions.
There's Oliver in the end.
I'd like to know the status of large area photon sensors, which might be very useful for, big Cherenkov, bottle Cherenkov, big scintillator detectors and so on. What is the status?
I would
Cheaper than photomultiplier.
I am afraid I cannot give you an answer to that. I don't know what the status is right there. I would imagine that it should be possible to use some of these ideas, in particular the wavelength shifting structures, to use cheaper structures or to combine imaging structures. So when I was talking about meta lenses, it was not just with the idea of doing a spectral dispersion, it's also with the idea of producing optics that can be at the level of a detector. So if I have a big detector, I should be able to build a very compact meta lens that would focus the light into a small structure itself, which means, of course, cheaper electronics, cheaper detection. Thank you.
Yeah, I have a question about this gem coated with graphene. Now it seems that you have to have graphene layers on all gem amplification layers. And then for the alignment purpose, all the holes of gem and the graphene are to be aligned. Now, how does this technology is there for graphene? Because I know for gem, the foils exist and one can make it. But for graphenes, do they exist or any comment on that part?
Yeah, so this is just the slide I skipped. The group at CERN is working on trying to use the gems that they're building. So these structures here to coat them with monolayers of graphene. Up to now, they encounter many problems. Obviously, a monolayer is difficult. So what they end up doing is several flakes. So multi-layers, 1, 2, 3, and they don't yet have the control of a sufficiently large flakes to cover the whole gem layer evenly. This is very active R&D.
Is it a part of this RD51?
Yes, exactly. And this is actually, I didn't mention it at all, but CERN has a quantum initiative, and that activity is part of the CERN Quantum Technology Initiative.
Okay.
So there's sort of an overlap.
Thank you.
Oliver was early.
So while there are other questions, we'll have to take them at lunch. With that, we will close today's session, and let's give a big hand to all the speakers who have contributed to this session.